Hello everyone. Today our topic is meter bridge. Let us discuss about the meter bridge. I'll show you the figure of this meter bridge. Here I have shown you the figure of this meter bridge. This meter bridge is based on the principle of Wheatstone bridge, which we have already discussed in our previous video. Now this is a meter bridge. Why it is called as meter bridge? Because it consists of exactly 1 meter wire that I have shown here between A and C. This is 1 meter wire which is marked with red color now. That is 1 meter wire. This wire, that is 1 meter wire, and it is of uniform cross sectional area, stretched taut and clamped between two thick metallic strips bent at right angles. Which are the metallic strips? I'll show you. This is one and this is the other one. Two metallic right angled strips, metallic strips. So in between these two strips, that is like L shape, in between them the 1 meter wire is stretched taut and clamped between these two metallic strips. The metallic strip has two gaps across which we can connect resistors. So I'll remove these marks and I will show one by one. First I have shown you the 1 meter wire. This is the 1 meter wire with the red color. Next, two L-shaped metallic strips which I am circling with the blue color, and then in between there are two gaps where we can connect the resistors. This is one gap, this is the another gap which I am marking with this green color. You can see them. The green circled one are the gaps between two metallic strips. These are L-shaped metallic strips. Then after that, the end points where the wire is clamped are connected to a cell. So this is the end points where the wire is clamped. It is connected to a cell which I am showing with the yellow color. Now I'll remove all the marks, then you will clearly understand everything. Red color which I have shown here is the 1 meter metallic wire. Blue color circles are the L-shaped metallic strips, that is right angled metallic strips. In between there are two gaps which I have marked with the green circles, and at the end of the meter wire, that is metallic meter wire, you have connected, you can see the battery is connected which I have shown with the yellow color. Now I will remove all these marks so that you can see the picture again. Now after that, in the middle point, exactly at the midpoint, that is between the two gaps, there is a point S. There is a point B. So here is the point B. From B, I'll remove the circle. From B, one galvanometer is connected. You can see there is a G like this. This is galvanometer. From B, galvanometer is connected, and the other end of the galvanometer is connected to a jockey. Other end of the galvanometer is connected to a jockey. What is this jockey? It is like one small rod like thing. It is just like our pen size, almost a small pen size, and it is a metallic rod. One end is a knife edge which can slide over the wire. That means you can keep this jockey on this wire, that is 1 meter wire, and you can slide it over that like this. You can slide it over the meter wire, okay, so that wherever it touches the wire, it makes a contact. That means a connection will exist. So a metallic rod, the jockey is essentially a metallic rod whose one end has a knife edge which can slide over the wire, and it will make electrical connection. So this is the introduction. So what is the introduction now? In the meter bridge we have 1 meter wire which is fixed between A and C in the figure. A and C in the figure. And then this wire is clamped between two right angled metal strips, which I will show with the blue color circles now. And in between the metallic strips there is gap. There are two gaps, that is where R and S are connected. And then after that, between A and C, a battery is connected. And then between B and D, a galvanometer is connected to a jockey. That is, galvanometer, one end is connected to B, other end of the galvanometer is connected to a jockey. Jockey is a small metal device, that's a rod like thing, which has a knife edge. One side it has a knife edge. It can slide over the meter wire so that it can make electrical contact or electrical connection. And then let's see what we can do with the meter bridge. Meter bridge can be used for so many purposes in the lab. You will do so many experiments using the meter bridge. You can find an unknown resistance. You can also find the resistivity of the material of the wire. And you can also prove series and parallel connection, that is combination of resistors. You can prove series and parallel combinations practically using the meter bridge. Like that you can do so many experiments in the lab. In this class your teachers will make you to study them and do practically in the lab. So let's start our discussion how we can find unknown resistance using a meter bridge. Once you know the value of the unknown resistance, you can also find resistivity of the material using its cross-sectional area and length of the wire. We can also find resistivity of the wire, because resistivity, you all know the resistivity formula also, you know, R is equal to rho L by A. Therefore from this you can find the resistivity also. And then you can also find series parallel combination. You can also prove series combination and parallel combination. Like that we can do many experiments. Now let's go and see how we can find unknown resistance using this meter bridge. So let us take an unknown resistance and connect it in the first gap. That is where R is here. I am marking with a black color circle here. Then in the place of R we will connect unknown resistance, and across the other gap we will connect known resistance, that is S. This is the known resistance. R is the unknown resistance and S is the known resistance. Then the jockey is connected to this point D, and the means jockey can slide over the wire. Then the jockey is connected to some point D on the wire. Now I'll remove these marks. From the end A, let us say at one point D it is connected. So I'll show you here with this green color. From A it is connected up to D. Then let us say that length can be L centimeters. From A to D, let us say it is L centimeters. Then because 100 centimeters is 1 meter, then from D to C, which I am marking with blue color, from D to C it will be 100 minus L centimeters, because 1 meter has 100 centimeters. If from A to D it is L centimeters, from D to C it is 100 minus L centimeters. Then already I told you unknown resistance we will connect at the place of R. Known resistance we will connect at the place of S. The jockey is connected to some point D on the wire at a distance L centimeters from the end A. Then the jockey can be moved along the wire. As I told you, it is as if we can slide it along on the wire, along this wire. Then let us say for 1 centimeter, the resistance is R centimeters. Then for 2 centimeters it is 2 into RCM. Then for L centimeters the resistance is L into RCM. Yes or no? Therefore for 100 minus L centimeters the resistance is 100 minus L into RCM. I hope you are following. Let us say, once again I am repeating, let us say for 1 centimeter the resistance is RCM. Therefore for L centimeters the resistance is L into RCM. Therefore for 100 minus L centimeters the resistance 100 minus L centimeters the resistance is 100 minus L into 100 minus L into RCM. So that is the resistance. Okay. So now you can see here I have explained everything in this notes. If RCM is the resistance of the wire per unit centimeter, then the portion AD of the wire has a resistance RCM into L. Then the portion DC has a resistance of RCM into 100 minus L. So now why we are taking the resistance? This meter bridge, already in the beginning I told you, it is based on the principle of the Wheatstone bridge. So we will make 4 arms of the Wheatstone bridge in the meter bridge. Therefore for 4 arms we are taking 4 resistances. These, like I have explained Wheatstone bridge in my previous video, you can see there it is like this. 4 arms are like this, A and then B, C, D. It is like this. This is the Wheatstone bridge. Between this is between A and C, we have connected a battery through a plug key that time, and then between B and D we have connected a galvanometer like this. There we have taken R1, R2, R3, R4, like this 4 resistances we have taken. In the similar way, AB, that is similar to the Wheatstone bridge, AB, I will show you AB. Now this is AB, from here to here it is AB, which I have drawn with the blue color. And then BC, BC means I have shown this, yes, once again I'll repeat, similar to AB, here I am drawing those lines. This is AB, that is I have shown with the blue color. And then next one is BC. Let's take the color. So this is the color, red is the BC arm. And then DA, let's take with another color, DA, that is the another arm, that is DA. And finally let's take the last arm, that is CD, yellow color. So AB is blue color, BC is red color, and DA is green color, and CD is yellow color. So 4 arms it has made here, AB, BC, DA and CD. With the resistances, the first one has R resistance, and BC has a resistance of S, DA has a resistance of L into RCM, and CD has a resistance of 100 minus L into RCM. like it is similar, exactly similar to a Wheatstone bridge. So if the jockey is moved along the wire, now once the connections are over, and then you connect the key, put the key, then the circuit is closed, current starts flowing. When the current starts flowing, I'll remove these marks on the meter bridge so that you can see the picture clearly. When the current starts flowing now, what happens is the jockey is moved along this wire, 1 meter wire. That is, when the jockey is moved along the wire, then at one particular position the galvanometer shows zero deflection. Galvanometer shows zero deflection. We call it as the balancing condition of the Wheatstone bridge. When the Wheatstone bridge is balanced, current through the galvanometer is zero. Then we call it as the balance condition. At the balance condition, R1 by R2 is equal to R3 by R4. This is called as the balancing condition. Therefore, in place of R1 in the meter bridge, we have R. So that is R, and in the place of R2, we have in the place of R2 we have that is L1 L into RCM. Let us take L into RCM, that is equal to R3. In place of R3 we have S, and in place of R4 we have 100 minus L into RCM. So this is the one. So rewriting it we will get R by S is equal to, this comes like this will go like this, R by S is equal to RCM into L divided by RCM into 100 minus L. So once again, this is the balancing condition of the meter bridge. R1 by R2 is equal to R3 by R4. So similar to that, I have taken the resistances. R1 means, once again I am repeating, here in the meter bridge capital R. R2 means between AD, that is L into RCM, then that is equal to R3. In place of R3 we have known resistance S, and in place of R4 we have 100 minus L into RCM. Then we will bring R and S to the left side. Then we will get R by S is equal to RCM into L by RCM into 100 minus L. Then where L is the point where we got the balancing point. That means current through the galvanometer is 0. Then RCM cancel. Then R by S is equal to L1 by 100 minus L1, where L1 is the balancing length. That is what I have shown here, which I am circling with the red color. So I'll remove all these things so that you can see everything clearly. So let us once again, we are applying the 4 ohms of the Wheatstone bridge to the meter bridge. We are applying 4 ohms of the Wheatstone bridge to the meter bridge, and we will get like this. How we are getting now? The 4 resistances of the bridge at the balance point then are RS RCM into L1, RCM into 100 minus L1. So the balance condition of the Wheatstone bridge gives R divided by S is equal to RCM into L1 by RCM into 100 minus L1. Then both the sides RCM cancel. We get L1 by 100 minus L1. This is the equation which I have put it in the rectangular box. That is, once again I am drawing with the blue color rectangular box. So this is the balancing condition for the meter bridge. So once you know the balancing point, that is the length of the wire L1, where you got zero deflection in the galvanometer, note that point and substitute that value in this equation, and you know the value of S and you know the value of L1, and finally you can find R1. We can find R from this formula which I have put in the black color box. That is, send S to the other side from this formula which I am circling with the black color, and send S to the other side, and what we will get is, we will get R is equal to S into L1 by 100 minus L1. Now this is the first time we have done this measurement or the reading. Then we can by selecting different values for S, we can repeat the experiment 5 to 6 times, or as per your teacher's advice. By choosing different values for S, we will read the note. We will note the readings in that galvanometer. Whenever we are getting zero deflection, we will note the value of L1. So every time we will change the value of S. Every time we will change the value of S, and we would get various values of L1 and calculate R each time. Each time we will calculate R, and finally we can take the correct measurement of R by taking the average, or however your teacher instructs. Then after that, how to minimize the error in R? You can minimize the error in R by adjusting the balancing point to the middle of the bridge. That means from middle of the bridge means half the distance will be 50 centimeters, because full wire is 1 meter. 1 meter means 100 centimeters. Therefore midpoint, if you take the midpoint as the balance point, approximately midpoint as the balance point, that error in value of R will be minimized. How can you do that? That you can do by selecting a suitable value for the resistance S. When you select a suitable value for S, you will get almost a perfect value for R. So with this, we can conclude how to find the unknown resistance using a meter bridge. It is very simple. We have applied the principle of Wheatstone bridge here, and we have taken the meter bridge and like the 4 arms of the Wheatstone bridge, and we have applied the same principle of the balance condition of the Wheatstone bridge and applied it to the meter bridge. We got this formula, that is R is equal to S into L1 divided by 100 minus L1. With this we can find the unknown value. Thank you for watching with this video. We will meet with another topic in the next video. Bye. God bless you all.